Hello, everybody, and welcome to our public key cryptography project. I am Sarah, and this is the rest of the team who worked on this project for the past 6 weeks.
My name is Lihem.
My name is Danny.
I'm Stuti.
I'm Jacqueline.
My name is Layla.
I'm Sophie.
My name is Darwin.
I'm Daniel.
I'm Xander.
I'm Fiki.
I'm SJ.
Okay, so what is cryptography? To put it simply, it is the science of secret communication. It is making a message secret by encrypting it or making it into a secret code. Only the person intended to understand the message can then decrypt the message. Say we have two people, Alice and Bob, and they want to share a message with each other without Eve, who is always eavesdropping. They don't want her to know what it is. So they could meet privately and come up with a shared secret key to encrypt and decrypt their messages, but this isn't always possible. Like, what if they are far away or communicating over the internet? This is where public key cryptography is used.
Thank you. So when we are addressing the issue of public key cryptography, we're talking about in the modern era where we're using computers and we're trying to send information over public channels. So for example, let's say I was trying to talk to my friend Daniel right here and I wanted to let him know, shout out to Daniel, and I wanted to let him know there are pineapples in the room across. The issue is my friend Asandam also just heard me tell this to Daniel, and so now Asandam can get pineapples in the room across. This is bad. Why? Because now Daniel can't get pineapples, and Asandam is going to get them when I did not want Asandam to get pineapples. So if we're just talking in a normal conversation, how would we normally go about fixing that? Well, there are several options. One is just to speak in a different language. One is to try doing like Pig Latin, or if anyone has seen Diary of a Wimpy Kid, they did like that one thing where they said like A at the end of every word. But then we also see with that, it is sometimes very easy to crack the code as to what cipher we're using. When we are using computers, the way we tend to do this is by using math, specifically by using one-way functions. This is where we get the idea of like public keys and private keys. Because a key, the relationship between a key and a lock is that a key is able to lock things and is also able to unlock things. So a public key will be using public information that, in this case, Eve would have access to, but it will be a really difficult math problem that only works in one direction. As in, you can use it really well to lock or encrypt information, but you cannot use it really well to undo what you just did. The private key will be information that is only available to Alice or Bob, and that will do the exact opposite of the public key. It will break down whatever the public key did and thus give you the original message. The way this gets accomplished is by using number theory, which is essentially a branch of math that has to do with integers and is particularly useful because we get to use primes. We will go into more depth about this later when we start talking about the actual math behind it. Be prepared, we're going to talk about math. But because primes, you can only break them down into one or the number itself, which makes it really easy to make really difficult math problems with it. The problem is, like I said, this gets really stupid difficult, so buckle up. It's gonna be a ride.
So now let's get into some of the examples of crypto systems before the public key cryptography was invented. So the first example shown here is the Caesar cipher, which many of you may have seen or even implemented before. The encryption process involves shifting all letters of the alphabet by a set number of places. To decrypt the message, Bob shifts all the letters backwards by the same number of places. In the example shown here, all the letters were shifted forward by 3 places. This crypto system requires that Alice and Bob share the number of places they're shifting by beforehand over a private communication channel, meaning that the Caesar cipher is not considered as a public key crypto system.
Okay, so I'm going to explain the Enigma machine to you guys. It was first invented towards the end of World War I, but it wasn't widely used until World War II by the Germans. And they used the Enigma machine to encrypt and decrypt secret messages. And this was very crucial for the German military because this is how they would communicate with each other without the Allies figuring out what their plans were. So the Enigma machine used a series of rotating wheels or rotors to scramble plain text into ciphertext. And ciphertext is like the encrypted message that they were sending back and forth to each other. And this is supposed to be really difficult to decrypt because if your Enigma machine isn't at the like exact setting, you're not going to be able to know what the message is. And this was like an unbreakable code for a pretty long time, but eventually the Allies were able to break it, and it significantly aided to the victory of the Allies in World War II.
So one of the main issues of the cryptic systems we had before PKC was the fact that you needed to meet beforehand in order to establish what the codes were. So this changed with James Ellis, Ralph Merkle, and Whitman Diffie and Martin Hellman. Essentially, the three of them found out about public key cryptography around the same time. James Ellis was the first. He worked for the British government, and the reason why most people don't credit it to him is because he could only release it after his death in 1997. The next person was Ralph Merkle, who was a student at UC Berkeley. He studied computer science, and although he was the first person to find it in public, he found it for his class, he released his paper in 1982, which was a couple years after Diffie and Hellman released their paper. This was incredibly revolutionary, and I have a quote up here. They started their essay with, "We stand today at the brink of a revolution in cryptography." Not only did this start a new field, cryptography, and assist with like giving number theorists a job, one of the main things it did was the US government did not like that this was being spread throughout other countries. So under the international tariffs and arms regulations, this was banned from being spread to other countries, and it would be treated as treason. So in protest, because they thought it was an overreach of government, what people would do is they would use this string, which basically explained how RSA worked in a line of code, and they would tattoo it onto their bodies, put it onto shirts, and then as soon as you take a flight, let's say from New York to Europe, suddenly you're treasonous against the United States. The issue with PKC is you need a way to actually implement it to transfer methods, and so they raced to find a practical use. The two things they found was RSA and Knapsack. Knapsack was only working for the first few weeks because it wasn't secure enough, and so they stuck with RSA until now. It's being phased out because of quantum computers and making it insecure.
So this is an analogy that I like to use to explain how public key cryptography works. Say Alice wants to send a message to Bob without Eve being able to see it. Alice puts her message in a box and locks the box using her private key. She then sends the message to Bob, who puts a second lock on his box using his private key. He sends the box with both locks back to Alice, who uses her private key to remove her lock. Then Alice can send the box back to Bob, where Bob can use his private key to remove his lock and now he's able to access the message. Notice how through this entire exchange, Eve wasn't able to gain access to the message because there was always at least one lock on the box every single time the message was sent back and forth. In cryptography, the locks are very hard math problems called one-way functions that are very easy for computers to do, but take a very long time for computers to effectively undo, which basically prohibits Eve from doing the math necessary to unlock the message.
So modulus is a part of modular arithmetic. Cryptographic algorithms use modular arithmetic to create encryption methods that are easy to apply in one direction, but difficult to reverse without specific information. This specific information is key to keeping the encrypted messages secure. So to understand how all this works, you need to understand what modulus is. So think of modulus like a clock. When you go past 12, you end up at 1. So let's say, for example, it's 10 o'clock right now, and you add 5 hours. You end up at 3 o'clock. So if we were to put all of this into a mod equation, the equation is A mod n equals R. A would be the dividend, and it would be 10 plus the number of hours added, which is 5. 10 plus 5 is 15. So 15 would be A. N would be the number by which A is divided to determine how many full times it fits into A. So n would be 12, our divisor. R is the remainder. When you add 5 hours to 10, it ends up going 3 past 12, so 3 would be our remainder. The full mod equation would be 15 mod 12 equals 3. This wraparound effect is why so many cryptographic algorithms are secure and efficient. Another part of modular arithmetic is congruence modulo n. Congruence modulo n shows how two numbers will leave the same remainder when divided by n. Two numbers, it basically says that two numbers are equivalent in a system where we wrap around after reaching n. There's two conditions in congruence modulo n. The first condition being that A is congruent to B mod n if n divides the difference of A and B. The second condition is A is congruent to B mod n if there exists an integer k that when multiplied by n and added to B, it equals A. We can do an example to make this more clear. Let's say A is 17, B is 5, and n is 12. We can use the first condition to prove that 17 is congruent to 5 mod 12. We know that n is 12, and the difference of A and B, 17 and 5, is 12. Now that we know that 12 divides 12, then we can say that 17 is in fact congruent to 5 mod 12.
So one of the really hard math problems that are used in cryptographic public key cryptography is known as the discrete log problem. Just as log x is the inverse of e to the x, a discrete log is the inverse of modular exponentiation. This can be seen in the form of g to the x, which is congruent to h mod p, where p is a very large prime number and g is a base. In this case, we'd write that x is equal to log base g of h mod p. So in simple terms, this problem is asking for the value of x that satisfies the previous equation. So if we look at an example, we can find that log base 3 of 4 mod 7 can be written as 3 to the power of x, which is congruent to 4 mod 7. The only way to solve a discrete problem right now is through brute force. And this example is in simple terms, but like in real life, these numbers would be way larger. After brute forcing it, we find that if x equals 4, we can write 3 to the power of 4 is congruent to 4 mod 7. Further simplifying it to be 7 divides 81 minus 4 using modular arithmetic. Further simplifying it to be 7 divides 77, which is true. So reasons it's used in cryptography is that if someone only knows the final number in the base, it's very hard for someone to reverse it because of how large the integers actually are. So this is why it's used in cryptography, because it's hard to reverse, and it's also why it's the basis of security for many public key crypto systems.
So, y'all are probably wondering, why does something as innocent looking as a to the x is equal to b mod n, right? So basically, what number can you plug into a to the x such that you'll have a remainder of b when you divide it by n? Why is that hard, right? Why does something that takes literally no space secure a lot of our crypto systems? That's what I'll be talking about today. But before we talk about why discrete log problems are hard, let's talk about why regular logarithm problems are actually very easy, right? So I'm sure somewhere in your math journey, you guys have seen something like 2 to the x is equal to 16. And I really hope most of you in the audience would say x is 4, right? Because 2 times 2 times 2 times 2 is 16. Now, you instantly calculated, so what you basically just did is you calculated the logarithm of base 2 of 16, right? If you did it so easily, who said ChatGPT can't, right? So even if we had something like 2 to the x is equal to 17, right? x would not be an integer, right? So it would be hard for us to get the precise value of what that exponent would be, but still computers can do this very easily. If you give your computer a quick Google search to find what 2 to the x equals 17 is, you'll get the result in literally less than a second. So what am I trying to say, really, right? I'm trying to say that standard logarithms are very well defined in mathematics. And the reason, and most computers use something, if you've taken a calculus class, they use something called the Taylor series to approximate logarithms. And basically, the reason why you can use the Taylor series on regular logarithms is because they have two very important features, right? They're continuous and they're differentiable. So basically, I'm not going to explain what those really mean, but it shows you that you can use calculus, right? You have a whole field of math to solve this problem. So because logarithms are very easy to compute, right? A natural question is, why do we have to add the mod n to this equation to make this difficult, right? Like exponentiation, alpha x is equal to beta, this would not be a good one-way function. So how would we make this a good one-way function? Well, what's making logarithms very easy to solve? It's because they have two features, right? They're continuous, like I said, and they're differentiable. So the idea is that cryptographers were like, well, if we can remove those two features that enable it to be solved so easily, then we would convolute the problem, right? Making it less straightforward. So how would we remove those two features, right, of a logarithm? What we do is we introduce modulus, like we talked about earlier, which is a very big field in discrete math. And in essence, what the modulus does is that in the first equation, x can be like 1.2 or like just not an integer. Now x is restricted to be an integer. So you have basically you have a discrete problem. And for y'all, if discrete is basically the opposite of continuous, right? So the amount of people in the audience is discrete because you can count them, right? But maybe your height is not discrete, right? There's not a fixed set amount of heights. There's infinitely many heights. So now that we know that adding mod n turns it into a discrete problem, which is less straightforward to talk about, we can look at why computationally solving these problems are hard. And what I mean by computationally is how long does it take for a computer to solve this, right? So to quantify the difficulty of solving a certain problem in cryptography or in computer science in general, computer scientists use something called time complexity, which is basically the number of basic operations it takes for a computer to solve a problem using a certain algorithm. So it's basically like this, right? Think about it as I'm walking to Tepper, right? How many steps did that take me, right? It's kind of like the amount of work that computers have to do. That would be my analogy. But we ask ourselves how much work do we have to do, or like how many steps, basic operations do we have to do in the worst possible case scenario. So we assume the worst possible case scenario for that problem, and then we ask ourselves how many steps do we have to take. So as you can see, I talk about the n-bit modulus, and what I mean is that when we're talking about the discrete log problem, like alpha x or equals beta mod n, right? We use mod n. So n is the modulus, right? And so if the modulus has n bits, that basically means, or I'll just use a different letter. If the modulus, so let me say we have a modulus k, right? And then if that modulus has n bits, so bits are basically just digits in base 2. They're like slots in base 2. Then to perform the modular exponentiation, so basically to go one way, it would take 2 to the n. It would take n basic operations I can talk about why if there's time at the end. But to unravel this, it would take 2 to the n steps. So basically, to compute the discrete log, it would take 2 to the n steps, right? So this might be confusing, but let me just make it easier to understand. Basically, what I'm saying is to compute alpha to the x is equal to beta mod n. If it took like 10 steps to do that, to find what x is, to unravel it, it would take 2 to the 10 or 1024 steps to undo it. So you can already see there's a large disparity in the amount of time that we go one way and the amount of time that we go backwards. Yeah, so that is why computationally solving the discrete log problem is a difficult problem.
So one of the commonly known public key crypto algorithm is known as the Diffie-Hellman key exchange. So to better explain this algorithm, let's say that Bob and Alice are trying to communicate secretly to each other, and there's an eavesdropper Eve. The first thing they do is agree on public parameters, where basically one is a very large prime number p, and the other is a base g that's in between 1 and p minus p. The next thing they do is Alice would select a random number, a private key that only she knows, and Bob would choose a private key, B, that only he knows. This would be between 1 and p minus 1 as well. After agreeing on their public parameters and their private keys, they would compute their public keys. So using the agreed upon base, G, and her private key, A, Alice uses the base to the power of her private key, mod P, to compute her public key. And this is derived in a way where it'd be computationally difficult to reverse it. Bob does the same thing with the agreed upon base G and his private key B. After they compute their public keys, they exchange them. So Alice gives her public key to Bob, and Bob gives his public key to Alice. So these keys are exchanged publicly, so an eavesdropper Eve would know what it is, but it doesn't compromise security because the numbers are so large. Once they exchange their public keys, they compute a shared secret key. So Alice takes Bob's public key and combines it with her private key to compute a shared secret using Bob's public key raised to the power of her private key, mod P. And Bob does the same thing using Alice's public key and his private key. As a result, despite using different keys, the mathematical properties of this algorithm and just exponential rules in general ensure that both Alice and Bob end up with the same shared secret no matter what their private keys are.
Let's go ahead and let's do an example of this. So we'll say that for the public parameters, we'll agree that P is 23 and G is 5. The private keys for Alice will be 6, and for Bob, it'll be B. These are keys only known to them. Once they switch, they'll do the computation that Studi just explained, and they'll end up with A as 8 and B is 19. Alice and Bob will exchange their public keys one last time, and they'll do the same math again to undo these numbers. At the very end, Alice and Bob will end up with the same secret key, which is 2.
So how Eve would be able to figure this out? The first step is Eve would have to intercept the public keys of Alice and Bob. Usually these are often denoted as A and B, but since these public keys are typically shared openly, this step is relatively easy for her. The next step would be to compute Alice and Bob's private keys. She would use the log functions in the context of the public keys she intercepted to calculate A equals log of A with base G to find Alice's private key, and B equals log of B with base G to find Bob's private key. Once she has obtained either Alice or Bob's private key, she can compute S, the shared secret. So S is equal to B raised to the power of A, which is also equal to G raised to the power of A times B mod P. Once she's figured out the equation, Eve now has a secret key. And that the secret key is what Alice and Bob use for secure communication. So now that Eve has it, she can potentially decrypt what they're saying and their messages.
Before we dive into Elgamal, we have to learn one more math concept called a multiplicative inverse. Multiplicative inverses are different from normal inverses. A number A's multiplicative inverse in the modular world of some n is U. When A and U are multiplied together, they are congruent to 1 mod n. This also comes with the caveat that the greatest common divisor of A and n has to be 1, and we'll explain why in a little later. So how does Elgamal work? Elgamal expands off of Diffie-Hellman. It also uses discrete logarithms, but Elgamal actually allows Alice and Bob to exchange a message rather than just a secret key. First, Alice and Bob publicly agree on 2 randomly generated parameters, a large prime called P and a value called G. Then, Bob randomly generates his private key called lowercase b and calculates his public key, capital B, so that B is congruent to G raised to the lowercase b power mod n. He shares this public key. Next, Alice randomly generates her own private key, called A, and computes two values. C1 is congruent to G to the A power mod P, and C2 is congruent to her message times capital B to the A power mod P. She publicly shares C1 and C2. Finally, Bob decrypts Alice's message by finding the multiplicative inverse of C1 to the lowercase b power times C2 mod P. This value ultimately equals M.
Building off of what Sophie was talking about on the last slide, here's an example of Elgamal. So first, Alice and Bob are going to create their publicly shared parameters, P and G. P is always a prime number. In this case, it's 23, and G is 5. So Bob is going to then choose his private key, which is going to be some random number, in this case 9, and he's going to use the public parameters that they previously made and his private key in order to come up with his public key, which anyone can see. Oops. Alice is then going to come up with her private key also, which is another random number, and use that and the public parameters in order to calculate C1 and C2. And notice C2 has 12 in it, and the original message that we are encrypting is 12. So she sends both of those numbers to Bob, which he can then use to decrypt the message. He takes the multiplicative inverse of C1, multiplies that by C2, and then takes the modulus of it, and our modulus is P, so 23, and he ends up with 12, which is the original message. Through this, Alice and Bob can use the two public parameters and their private keys to calculate the original message. And Alice, without the private keys, it's impossible for her to calculate the original message.
All right, so now we're going to be talking about another PKC algorithm. So basically, you want Alice and Bob to communicate over an insecure channel, but you don't want someone like Eve to eavesdrop and intercept her message. And this PKC algorithm is called RSA. So this equation, right, m to the e is congruent to c mod n. That should be a congruent symbol, my bad. But this is familiar, right? It looks like the discrete log problem. So interestingly enough, RSA and Diffie-Hellman use the same form of equation to secure their information. The only thing that differentiates them is what variables are known in this equation. So in Diffie-Hellman, remember we were talking about how it's secured by the discrete log problem. So basically you have to crack that problem in order to break this crypto system. We were talking about that. M, C, and N are all known. So basically in Diffie-Hellman, you need to find that E. You need to find that exponent. And in RSA, however, it's a little bit different, right? So M, the base, that's not known. E is known. And the remainder, C, is known, and the modulus is known. But you're now trying to find what that M is. If you can find what that M is, then you can make the crypto system insecure. And you've noticed that I've used different letters here, but they have a purpose. So you're going to see later in an example that M is a message, because messages are really just numbers. And E is the encryption exponent, C is the ciphertext, and N is the modulus. So now we'll be performing an example right now.
Okay, so why does RSA work? So it was explained in the previous slide that there is a number n, right? Imagine n is just a very large composite number. Now this n happens to be made up of two prime numbers that have been multiplied. it is very difficult for even our best supercomputers to factorize and back into its prime components. In fact, while there is a known method, it will take potentially millions of years for our best supercomputers to achieve such a feat. Now, I would like to draw your attention to the image on the right, which shows prime factorization. Now, this may not be exactly how factorization works in RSA, but it shows the difficulty of such a feat regardless. So in this image, we have an 8-digit number being factorized into prime components, right? Now, RSA has 309 digits, or 1024 bits. So if this image looks difficult to solve, RSA is potentially infinitely more difficult to solve. Now, I would also like to draw your attention to the image on the left. So the image on the left is a generated private and public key. The private key is the one on the left, the public key is the one on the right. So a private key is going to be much bigger than a public key because the public key is just a public key. It holds just nothing special. It's what everyone's going to know. But the private key holds not just the information from the public key, but additional information that Eve will not be able to figure out. Only Alice or Bob will know the information that is in the private key.
So now let's implement RSA with an example. So here, the information has been organized into 3 columns: information private to Alice, information private to Bob, and public information that Eve, the eavesdropper, can access. So we start off with M, and this represents the message that Alice wishes to send to Bob. We let that equal to 65 in our example, and this stays private to Alice for now. On the other end, Bob comes up with 2 primes, P and Q. In a real-life RSA application, these 2 primes would have to be very large for security. I'll explain later why more digits and larger primes means more security, but for now, for simplicity, we're going to use the primes of 61 and 53. Bob then proceeds to calculate the product of these 2 primes, denoted by n. This product comes out to be 3,233 in this example. Bob then publishes this as public information so that Eve can see this. Next up, Bob calculates P minus 1 times Q minus 1. This turns out to be 780 in this example, and it has to stay private to Bob. Next up, Bob comes up with E, which is the encryption exponent. E has to satisfy the condition that the greatest common divisor of E and P minus 1 times Q minus 1 is 1, meaning that the 2 numbers have to be relatively prime. In this example, Bob has picked the encryption exponent of 17, and it satisfies this condition because the greatest common divisor of 17 and 780 is indeed 1, because they're relatively prime. This information gets published as public information so that Eve can see it. And lastly, Bob calculates D, and D is the multiplicative inverse of E, mod P minus 1 times Q minus 1. In this example, the multiplicative inverse of 17, mod 780, comes out to be 413. D stays private to Bob. And on the other end, Alice calculates C, and C is congruent to m raised to the power of E mod n, meaning in this case, C is congruent to 65 raised to the power of 17 mod 3,233. In this example, C comes out to be 2,790. Alice sends this over to Bob, meaning that Eve will be able to see it. The last step that Bob performs here is raising C to the power of D. And this is congruent to the message itself in the mod n. And as you can see, if we raise 2,790 to the power of 413, it is going to be congruent to 65, mod 3,233. I will explain later why this is the case, the math behind how we were able to get to this congruence statement. But for now, let's talk about why the primes need to be so large. So suppose that the primes are not very large. This means that from n, which is published so Eve can see it, Eve will be able to easily factor it into its original factors of p and q. Upon obtaining p and q, Eve will then be able to calculate p minus 1 times q minus 1, which was the 780 in our previous example. After obtaining this, Eve will be able to calculate the multiplicative inverse of E using mod 780. And Eve will thus be able to proceed to access the message. Now, to prevent this from happening, we need to make sure that Eve is not able to factor n into its original factors. So Bob needs to come up with primes extremely big so that it'll take Eve an impossibly long amount of time to figure it out. Now, how big do we mean? So previously we discussed that in base 2, these primes need to be 1024 bits. So what this means is that it needs to have 1,024 digits, or 2,048, or even 4,096 digits. What this means in base 10 is that it needs to have hundreds, even thousands of digits. And as you can imagine, when you multiply two numbers of such great magnitude together, it will be very hard to factor them into its original divisors. Now, let's discuss that last step, why c raised to the power of d is congruent to m mod n. So we start off with the definition of c. C is congruent to m raised to the power of e mod n. This is true because that is exactly how Alice was able to calculate c. We then raise both sides to the power of d. Now let's remind ourselves of what d is. D is the multiplicative inverse of e in the mod of p minus 1 times q minus 1. This means that e multiplied by d is congruent to 1 mod p minus 1 times q minus 1. We can then rewrite that as e times d
is equal to k, and k is an arbitrary integer.
It's equal to k times p minus 1 times q minus 1 plus 1. Now, if we take a look at our equation on the left, we can see that m is raised to a power of ed. We can substitute that ed with what we have obtained on the right side to get this equation here. If we take a look again at the exponent of the m, we can see that plus 1, and we can change that into times m, as shown here. The next step would be to take a look at the first term, and then raise m to the p minus 1 times q minus 1, and raise that whole thing to the power of k. Now we're going to introduce Euler's Totient theorem. This theorem states that when we raise a to the power of phi of m, and I will explain what phi, which is the totient function, is later. But when we raise a to the power of phi m, it'll be congruent to 1 mod m when we have a pair of integers a and m, so that the GCD of a and m is 1. The phi function of m means the number of integers less than m that is relatively prime to it. Now imagine we insert a prime p into the phi function. What do you think would be phi of p if p is a prime? Of course p minus 1, because p is a prime, so any number less than it would be relatively prime to it. Because remember, the definition of being relatively prime is that the GCD of those two numbers is 1, and primes have only factors of 1 and themselves, so any number that is less than it will only share a factor of 1 with it. So the phi of p will be p minus 1 for a prime p. Now, if we consider two distinct primes, p and q, then we can say that the phi of p is p minus 1, the phi of q is q minus 1. Then we can intuitively imagine that the phi of p multiplied by q will be equal to p minus 1 times q minus 1. This is not a rigorous way to see why the phi of p times q is this value, but it is definitely an intuitive way to see it. And if any of you have a question about how to do it rigorously, I will discuss it in our last section. So, if we take a look at our equation on the left, we can see the p minus 1 times q minus 1 in the exponent. So, we can replace this with phi of p times q. And if we take a look at Euler's totient theorem, the phi of p times q, which is the phi of n, because remember, n is equal to p times q. If we take a look at Euler's totient theorem and apply it to our case, the a in our case will be m, and the m in the equation written up there will be our n. So m raised to the power of phi n will be congruent to 1 mod n. This is exactly what we need. So in our equation on the left, we can replace m raised to the power of phi n with a 1, as shown here. We know that 1 raised to the power of anything if k is an integer will be 1. So this will cancel out, resulting in our final equation of c raised to the power of d is congruent to m mod n. And that is the math behind how the last step of what Bob does works in RSA.
So now we're gonna talk about how cryptography research works. Now that it's important to know how cryptography research works because we've just gone through 3 different crypto systems, those being DV-Hellman, Elgamal, and RSA. And we've gone through a lot of the math and nitty-gritty behind it, and it's good to see how the research works that goes behind it. And in its simplest terms, cryptography research is really just a battle between computer science and number theory. In computer science, we're basically just designing our crypto system and that we think can't be broken, we think it's secure. And then over on the number theory side, we have people trying to come in and get our crypto system and try to break it. And if they can't break it, then the crypto system is good and secure and it's ready to be implemented. And the research process starts by first identifying the problem with identifying some problem in cryptography. So this problem could be numerous things, and it could be an example of, it can be a problem with the current crypto system, or it can be a problem with cryptography overall, where like new ideas or new technologies are coming out that threaten the crypto systems that we use today. And once we've figured out what our problem is, we have to find a mathematical concept that is applicable to our problem that can be used for cryptography. So this is usually something that is hard to generate. It's easy to generate, but it's hard to revert back. An example of this would be the discrete log problem, or it could be something else new, a new theory that you come up with that is best for your crypto system. And once you figured out that concept, you have to design a crypto system around that concept. So when you're designing your crypto system, you have to figure out what information you're sending over the public channels and what information you're keeping private to Alice and Bob. And then you figured out what information you're sharing. So once you figure that out, you use usually equations to figure out how you're going to encrypt your message, and then you're going to figure out how to send it, and then you're going to encrypt it. You're going to decrypt it. And you have it designed, and you're now going to send it over to be tested. So when you have a crypto system, you can't just say, oh, I think this works and good, and ship it out. You actually have to have people test it to figure out that it actually is secure. So this is kind of like a back and forth where you have your design and you test it. And when you test it and it breaks, then you have to go back and redesign your crypto system. Or if there's a flaw in your math entirely, you have to go back and find some sort of new math that will work better than what you had before. So this kind of cycles for a while until you actually have something that's secure. And when you finally do have a secure crypto system, you go to implement it into the real world. When it's implemented, it's out for anybody to use and anybody to see. And so you have some of the brightest minds trying to crack this so they can get the data that you're trying to share privately. And this is where the whole research process kind of cycles, because whenever somebody figures out that I can break your system in this way, you have to be, okay, I see that, and then you have to go back and redo the research process so that you can develop a new, better crypto system in the future. And an example of a current day problem would be the development of quantum computers and how they're threatening our current crypto systems that we use to protect our data right now. And then we're going to have SJ come and introduce us to that.
All right, so quantum computers are going to be a big threat to crypto systems. But first, what exactly are quantum computers? So let's compare a quantum computer to a classical computer. A classical computer uses bits, right? And a bit can be represented by either two values, 0 or 1, on or off. But a quantum computer uses what's called qubits. And qubits are actually able to represent both 0 and 1 at the same time. This is because of something called superposition. Now, superposition in quantum mechanics is very, very complex, but the gist of it is that it's a system that it's an idea that allows for a system to represent two states at the same time until it is measured. That's the whole idea behind Schrodinger's cat, for example. The cat that's both alive and dead in the box until you open the box. So I would like to draw your attention to the image on the right, as that shows how exactly superposition works in qubits. Now, for the image on the left, that is actually Finland's second quantum computer. Their first quantum computer was designed in 2021, and it has 5 qubits. This quantum computer was designed last year in 2023 and has 20 qubits. Now, none of these current quantum computers are powerful enough to solve our biggest computational issues, but such quantum computers are expected to arrive by 2035. So, an example of what quantum computers can do that classical computers can't is something known as Shor's algorithm. Shor's algorithm is basically just a quantum algorithm that's designed to factorize large integers, like the ones that we'd see in RSA. So basically, that means that when quantum computers come around, something like RSA, it's pretty much the anti-RSA. It's completely going to break the system. Now, I'm going to hand the microphone over to Danny, who will explain what quantum proof crypto systems researchers are developing.
Now that we've discussed quantum computers, let's talk about the threat. We know that once quantum computers come out, our current data protection methods will become outdated, like RSA and AES. Groups at the forefront of this research are currently developing post-quantum cryptographic algorithm with the goal of standardizing new encryption methods. This innovative security approach will focus on establishing new security standards across the board. Groups that are working on this are Google, IBM, and Microsoft. There are 3 main ideas that almost all researchers are agreeing upon right now. The first one is isogeny-based crypto systems. Imagine a maze-like structure which only one person with the secret path knows and can navigate quickly. Even quantum computers will have a hard time getting through this. Likewise, there's lattice-based cryptography, which essentially creates a 3D tic-tac-toe board using a bunch of grid points. To unlock the data without the secret key is incredibly difficult, and you would need to undo all the complex math we just covered. The third and final idea that is being discussed right now is expander graphs. Imagine a web of points that is so dense it resembles a spider web. The complexity makes it difficult for even quantum computers to find the right path through, and this will take an indefinite amount of time. Thank you.
Do we have any questions about the presentation? Yeah. Yeah, so like, for example, Diffie-Hellman talking over something that's insecure as the internet, right? So Diffie-Hellman is literally everywhere in your computer. Like when you open up your computer, you're on the internet. You want, like, let's say you're texting someone, right? So really what messages are is every number is mapped to a certain value, right? So basically what I'm trying to say is that a message can be converted to a number. So that's how you can use something like Diffie-Hellman to communicate with your friend on like the internet. So like for example, if you use messages, you talk to like maybe your mom, right? That's still on an insecure channel, and Diffie-Hellman would come into play. So that's like a very modern day example.
There's also a recent case where two nations, I believe one of them was Pakistan and another country, where they were trying to exchange messages, and it like was a really political thing. So they had to do like secret messages, and also our government agencies also use Diffie-Hellman all the time to communicate with each other.
You have more questions? There's like 5, right?
So basically, quantum computers are very, very rare. Even quantum computers are not only weak, but they only exist in like first world countries. Basically, with our best researchers and scientists working on them. Like there is none available to like the public right now. That's coming in like many years to come.
Has 20 qubits. That sounds like a small number to me, considering like classical computers. Is that current computers still able to like break these algorithms, or is this like something that we're only going to see in the future?
So current computers can break this algorithm. Otherwise, we would be cooked because Diffie-Hellman is literally everywhere. So my answer to that would be no. But the idea is that as we get more research into quantum computing, we can build these super really fast computers that can do these operations like really quickly. And the idea is that once you have these quantum computers emerging, then you'll have a number of theorists trying to create harder math problems. And so the cycle sort of ping pongs back and forth. I guess that's how people make money in the field, right? So.
Yeah, so you mentioned that 20 qubits, it seems like a very small number to you, right? You're precisely right. It is a very small number. So yeah, it's no quantum computer, like Fiki said, no quantum computer exists that can break these algorithms, but all of them show great potential. All of them show that they are immensely faster than our best classical computers, and they can even rival supercomputers in some cases, right? And you have to take into account that supercomputers have a lot of many more bits inside them, right? And so if a quantum computer with only 20 qubits is able to rival a supercomputer, just imagine what it's going to be able to do with more bits, more qubits.
And also, one thing I want to say is we talked about it has 20 qubits, right? But you can hold two states at the same time. So the idea is that that's sort of like representing like 2 to the 20 like pieces of information, I would imagine. So you would need less qubits to match the same level of speed and security as a regular computer because you're able to hold 2 at the same time.
It essentially goes off an exponential graph. Like, you mentioned normal computers, they can't do the same problems because normal computers do things in a linear manner. They'll do step 1, step 2, step 3. Quantum computers will do step 1 through 10 at the exact same time. So if I give you like 1 to the power of 100, that graph is how a quantum computer works. It will be forever exponential.
Any more questions? Thank you, everyone.